Let's talk about measuring the impossible. I mean, really, truly impossible things. Stuff you can't get to, can't touch, can't put a tape measure on. Well, it turns out there's a secret tool for that, one that's ancient, but is still powering some of our most futuristic technology.
So just think about that for a second. How on earth do you find out how big something is or how far away it is if you can't physically get to it? It feels like a riddle, right? A total paradox.
You know, like a kite. You're flying a kite, it's way up there. You know exactly how much string you've let out, sure. But how high is it? Like straight up from the ground. How do you figure that out?
Or maybe you're standing on a cliff, looking out at the ocean. You see a ship on the horizon. How far away is it exactly? You can't exactly swim out there with a measuring tape.
And it's not just things that are far away. What about the Leaning Tower of Pisa? We all know it leans, but by how much? You're not going to just, lean a giant protractor against a priceless historical landmark. These are all problems of the unreachable.
Well, the answer, the incredibly elegant key to unlocking all of these puzzles, is hidden in plain sight. It's the triangle. Seriously, the humble, three-sided triangle. If you understand its secrets, you can measure just about anything.
All right, let's open up the toolbox. First up, we're going to start with the basics, the absolute foundation of all of this. We're talking about the right-angled triangle. This is your first and most important set of tools.
And the magic word you need to know is SOHCAHTOA. It sounds kind of funny, but it's the key that unlocks everything. It's just a simple way to remember how the sides of a right-angled triangle relate to its angles. Sine is the opposite side divided by the hypotenuse. That's the long one. Cosine is the adjacent side over the hypotenuse. And tangent is the opposite over the adjacent. That's it!
Now look, if SOHCAHTOA is a bit too abstract for you, our source material has another one that's, well, it's pretty hard to forget. Some old hags cackle and howl till old age. Hey, whatever works, right? The point is to get it stuck in your head, because this is the bedrock of everything we're going to do.
Okay, let's make this real. You've got a 12-meter ladder. You lean it against a wall, and the bottom of the ladder is 2.5 meters away from the wall. So what do you see? You see a right-angled triangle, right? The ladder itself is the hypotenuse, so we know two of the sides. And with a little something called the Pythagorean theorem, we can find the third. And just like that, boom, the ladder reaches 11.72 meters up that wall. See? A real-world problem solved.
That's all great for perfect corners and straight walls. But the real world is messy. It's not always made of perfect 90-degree angles. So what happens then? Well, it's time to upgrade our toolkit.
I mean, really, what do you do? The triangle in your problem is wonky. It doesn't have that neat little right angle in the corner. Suddenly, your trusty SOHCAHTOA doesn't work. Are you just stuck? Is it game over?
No way. You just need to pull out the bigger tools. And here's your guide for which one to grab. If you know a couple of angles and a side, or maybe two sides and an angle that's not squished between them, you're going to want the sine rule. But if you know two sides and the angle that is stuck right between them, or if you know all three sides but no angles at all, then you reach for the cosine rule. It's like a decision tree for solving any triangle. And this right here, this is the whole shebang. With your basic SOHCAHTOA for the right-angled ones, and the sine and cosine rules for literally everything else, you are unstoppable. There is no triangle out there, no matter how weird its angles are, that can hide its secrets from you.
So now we've mastered triangles on a flat 2D surface. But we live in a 3D world, so let's take everything we've learned and build something with it. This is where it gets really cool.
So look at something like a pyramid. It's a complex 3D shape. But the trick is to slice it open in your mind and find the simple 2D triangles hiding inside. We can actually draw a right-angled triangle right through the middle of it, using the pyramid's height and half the width of its base. And once we've done that, we're back in familiar territory. We just pull out our old friend SOHCAHTOA and solve for whatever we need. It just goes to show you, even the most complex shapes are just made of simple ones we already know how to solve. Okay, so we've got all these tools, we've got these rules, but let's be real. This isn't just a math class. What we've been talking about is basically a real-life superpower.
Hey, remember that kite from the beginning of our chat? The one we couldn't measure? Well, with a 65-meter string at a 57-degree angle from the ground, we just plugged that into our SOHCAHTOA toolkit, and the answer is 54.6 meters. Just like that. An unreachable height, perfectly measured.
And that's really the big idea here.
This is so much more than just remembering some formulas for a test. It's like getting a new pair of glasses. It's a lens that lets you see the hidden structure, the invisible geometry that holds the entire world together.
And I'm not exaggerating. This is the math that architects are using right now to build skyscrapers that touch the clouds. It's what sailors and pilots use to navigate the globe. It's literally the code that builds the stunning 3D worlds in your video games. And get this, it's how astronomers measure the mind-boggling distances to other stars.
So, from a simple ladder leaning against a wall all the way to the farthest reaches of space, it all comes back to the triangle. It's a tool that lets us map our planet, build our civilization, and even reach for the stars. So the only question left is, what will you measure?